we will have a presentation from Dr. Andy Sellars. He's one of the founding members of this organization in UK. And personally, actually, I met him in July in Brussels, in the Compound Semiconductor Conference. And he expressed his high interest in visiting Taiwan. He's so excited. And so he said, we should give you a lot of good things about our company and our organization in this talk. However, I think due to some technical challenges, he won't be able to make it, all right? So, but he still delivered his speech through the video. So let's listen to that. Unfortunately, there's no interactive Q&A, right, as far as I know, right? So let's listen to his story. But before we go this, actually, I read his personal bio. He was the film lighting specialist in the 007 movie. Okay, that's one of the quite experience for his past life. But how he become an expert in this compound semiconductor industry, let's listen to his story. Thank you.
Hello, I'm Andy Sellars. I'm Strategic Development Director with the Compound Semiconductor Applications Catapult. And today I'm going to give a presentation on a strategy for growth in power electronics and optoelectronics. So firstly, the Catapult is a research and technology organisation, part of a network of catapults established by Innovate UK over the last 10 years. There's actually 9 catapults in the UK, focusing on different areas of technology. We have a cell and gene therapy catapult based in London. We have a high-value manufacturing catapult, which has 7 research and technology centres across the UK. These catapults are non-profit research and technology organisations aimed at growing the economy in their various sort of different technology areas. My catapult in particular focuses on the application of compound semiconductors, and we are based in South Wales and operate across the UK. The Catapult network actually represents an investment by UK government of about £1 billion across the network. So a little bit of a timeline for the Catapult. We did some consultation between about 2013 and 2015, looking at the industry and the academic investments that had gone in to the area of compound semiconductors, and put together a business case which was submitted to Treasury in 2015. The Catapult was announced in early 2016, and we've been operational really since about 2018. We moved into our state-of-the-art facilities in 2019, and in fact, had an official opening with the Royal Society in 2020 and signed a memorandum of understanding with ITRI in Taiwan in 2020 also. So we're very keen to sort of capitalise on that. Now, the strategic direction for the Catapult, our vision is for the UK to become a global leader in developing and commercialising new applications for compound semiconductors. And this graph on the left-hand side represents our sort of focus areas, if you like. So on the y-axis, we have market attractiveness, and on the x-axis, we have capacity to exploit that market. And you can see these are actually color-coded. So the blue represents power electronics, the topic of this discussion, and the red represents optoelectronics. And you can see that the size of the markets are significant. Typically, a power electronics in transport market is an $18 billion market, and a photonic for digital economy is an $11 billion market. So these are sort of our primary focus areas. And since inception in 2018, our sort of main priority area has been net zero and vehicle electrification. Since 2021-22, our next focus area has been on future telecom networks. And now we are starting to look at sort of the next area of opportunities in terms of net zero smart energy grids, and also horizon scanning for future opportunities in quantum and healthcare. So a little bit about net zero and why that is applicable to compound semiconductors. Well, electric vehicles reduce carbon dioxide emission at the point of use, although effectively what they're doing is they're transferring the generation of CO2 back into the electricity network. At some point, you have to generate electricity if you're going to run electric vehicles. And in order to become carbon neutral, the way in which we're going to do that is through renewable energy sources. Now, renewable energy sources are generating more and more electricity each year. The UK is in a very strong leadership position with offshore renewable energy. But the trick about renewable energy sources is that they generate electricity when it's either sunny or windy. And that energy has to be banked at the point of generation and then has to be transferred and delivered to the customer at the point of need. And that requires flexible energy grids. And this is a strong area for growth in power electronics, specifically using compound semiconductors. And in future telecom networks, a similar story really. Future telecom networks, the 3G and the 4G network is predominantly built using what are called macro cell base stations with very large area coverage. As we move to 5G and 6G and beyond, in order to get the data rates up and the latency down, there's likely to be a much stronger move towards small cell base stations. As you put more data into the base station, it creates increased capacity, and that capacity has to find its way into the network, and it does so through a technology called backhaul. Equally, small cell base stations are very good for high density urban environments, but for low density rural environments, we see a much larger role for direct satellite communications. As we move towards more and more data and more services operating on the network, there is an increased need for cyber resilience and quantum encryption. And also, at the moment, the telecom network consumes something like 3% of the global energy resources, and it's forecast to get to about 8% by the end of the decade. So clearly, there is a need to make the network more efficient in order to drive down those energy costs. And all of these things require compound semiconductors. So if we look at an electronic system, and we just look at where semiconductors take place in that electronic system, when building an electronic system, you always require three types of semiconductor. You require a silicon semiconductor, which is typically 70 to 80% of the cost, a compound semiconductor, which provides some specialist functions, which is typically 10 to 20% of the semiconductor value of the product. And there's another category which provides things like display functions, and they're typically sort of 5% of the semiconductor value. And I've just sort of broken down some typical examples here. An iPhone with a manufacturing cost of $570 has a semiconductor value of about $350, and the silicon represents about 80% of that value. Compound semiconductor about 10%, and the other about 10%. And you can see there's a similar story for the Tesla powertrain using power electronics. Again, manufacturing cost about $3,900, semiconductor value about $1,900, silicon proportion about 20% in that case, and the compound semiconductor a higher proportion because of the electric powertrain. So there's a significant opportunity for compound semiconductors in these new application areas. So importantly, compound semiconductors outperform silicon semiconductors in these three areas: power, speed, and light. So power, the application is for electric vehicles, smart grids, as I mentioned earlier, and they will predominantly use the main compound semiconductors being gallium nitride and silicon carbide. Speed, satellite communications, increasingly will require compound semiconductors such as gallium arsenide and gallium nitride. And the generation and detection of light for imaging and quantum and telecommunications require compound semiconductors such as indium phosphide. And I put in another example here of cadmium telluride. So the key markets for the Compound Semiconductor Applications Catapult are not surprisingly net zero, future telecoms, and intelligent sensing. And actually, within the Catapult, we are structured in terms of 4 delivery teams. We have a power electronics team, we have an RF and microwave team, we have a photonics and sensors team, and we also have an advanced microelectronic packaging team. And these 4 teams will work very effectively to deliver future technologies exploiting the benefits of compound semiconductors. We have an innovation centre, about 30,000 square feet or 3,000 square metres in metric, around about 100 researchers, engineering and support staff. Within the innovation centre, we have a design studio where we can simulate and model the various aspects of the applications for compound semiconductors. We have a class 10,000 advanced microelectronic packaging lab where we can take semiconductor die and package them up by adding interconnect. We have a power electronics laboratory, an RF microwave laboratory, and a photonics and sensors laboratory where we can test out the prototypes that we're helping companies to develop. So actually, where does the Catapult operate within the supply chain? So this graph actually represents a supply chain taking raw materials and actually out to produce an end application. And it's a typical sort of semiconductor supply chain. We take raw materials, we process those raw materials to create a wafer. We then etch chemicals into that wafer in order to produce a die. The die is then singulated. And electrical connections are added onto it in order to create a module or a chip. The chip is then incorporated into a system, and the system ends up finding an end application. And I've just given 3 examples here of automotive, telecom, and space quantum applications. Typically, the value of the supply chain, as you move through the supply chain, typically the value increases by an order of magnitude as you go along. So I've indicated here $1 becomes $10, becomes $100, and so on as we move through the supply chain. And the Catapult actually has very effective reaches across the supply chain in terms of convening companies at the beginning, wafer fabs, and also working very closely with companies at the end of the supply chain in the automotive and the telecoms industry. But specifically, our sort of technology focus is in the die-to-system area. That's where we add the most value in these in the projects that we're working. So I've mentioned that whenever you're building an electronic product, you need 3 types of semiconductor. You need a silicon semiconductor, a compound semiconductor, and quite often you need another type of semiconductor as well. And I've just given some examples here. Silicon semiconductor is always used to produce the high functionality microprocessor that runs the software and provides the intelligence for the product. The compound semiconductor quite often provides is used to produce power transistors, RF amplifiers, and photonic communication functions. And the other is quite often used in more bespoke areas such as displays or even sort of novel sensors, which are starting to emerge at the moment. Now, we've looked at kind of the UK capability across these different sort of semiconductor types. So this is a snapshot, a heat map, if you like, of UK capability in silicon. And we're actually sort of broken down silicon in terms of the lithography. So we have legacy silicon, mainstream silicon, and leading edge. Legacy being typically sort of 90 nanometers and above, mainstream being 28 to 90 nanometers, and leading edge being less than 28 nanometers. And you can see across this, what we've looked at is UK capability in research development, design, fabrication, and also kind of an analysis about the strategic importance of these different silicon nodes. So research development, UK is very high at legacy, and some moderate research development in the mainstream and leading edge processes. When it comes to design, UK is very, very strong at mainstream and leading edge design, with perhaps the second highest number of design companies, second to the United States. When it comes to fabrication, we have many fabs capable of legacy design. We don't have very many fabs at all, in fact, in the mainstream and the leading edge. When it comes to strategic advantage, arguably the mainstream and the leading edge silicon nodes are critical to strategic advantage. Now, I've done a similar analysis for compound semiconductors, and these have been broken down by power, speed, and light. So in compound semiconductor, we have power electronics, RF microwave, photonics, and quantum. And again, we've looked at the UK capability in research and development, design, fabrication, and strategic advantage. And here in research and development, actually, the UK is very, very strong in power electronics, RF, and photonics, primarily due to investments made by the Engineering and Physical Research Council across the past decade. Something like £1 billion of investment has gone into power electronics, RF, and photonics. And you can see the numbers here in the presentation. In the design space, UK is very strong, again, across power electronics, RF, and microwave. We have lots of startups, lots of SMEs, and 1 or 2 large companies operating in that space. In fabrication, we have some sort of smaller and medium-sized organizations. So we have sort of a mix there, but a medium capability, if you like. And strategic advantage, I think we would argue that all three of these areas are important for strategic advantage. Power electronics, specifically for electric vehicles, net zero, smart energy grids. RF and microwave is critical to future telecom networks and defense applications. And photonics is critical to telecoms, quantum, and defense applications. So we see there's a very strong strategic advantage across the piece there. And we've also looked at UK capability in this other category of semiconductors. So specifically looking at sort of OLEDs, perovskites, thin film, and 2D. There's a bit of a mixed picture here. Quite often very good capability in research and development, in design, particularly in thin film and 2D, very, very strong capability with lots of companies emerging out of the university base. And in fabrication, actually some world-leading fabrication. These technologies tend to be sort of quite early stage. So when it comes to strategic advantage, it's quite difficult to assess in some ways. These early stage technologies could be very, very disruptive. And so we're sort of certainly keeping a very close eye on them. So how does this sort of factor in to collaboration? How do we collaborate and work with companies, internationally with companies? Well, actually, in 2020, the UK government published the Integrated Review, which sets out a framework looking at different technologies. I put a link here in the presentation. And this kind of framework describes three approaches in terms of own, access, and collaborate. And it suggests that, in terms of where the UK has a leadership and owns the research development, the design and the fabrication, then that's kind of an own category. That's an area where perhaps UK can demonstrate ownership and leadership in that particular space. But as you saw from those heat maps, quite often there's a sort of a mixed picture. Now, I don't think that's unique to the UK at all. I think that that's kind of very, very similar to other advanced economies. Advanced economies have tended to focus on one particular area and develop one or two particular strengths. And so therefore, it's important that we look about the access and the collaborate. And the access is where the UK will seek to acquire some critical science and technology through options, deals and relationships. And the collaborate is where the UK can provide unique contributions that allow us to collaborate with others in order to achieve our strategic goals. So this framework is a very helpful framework in order to work out how we collaborate with international partners. And I've come up with I've just sort of presented here some ideas, some sort of thought process about how we will collaborate in order to drive the markets, as at the beginning said, about power electronics and optoelectronics. And this is about looking to scale up to address these key large markets that I described at the beginning of the presentation. So specifically, we see a great opportunity for collaboration in integrating compound semiconductor die into producing advanced modules for net zero and electric vehicles and smart energy grids. Some heterogeneous integration, combining silicon die with compound semiconductor die to produce advanced modules for telecoms, cyber and artificial intelligence. And again, some other examples here about hybrid integration to produce advanced modules for space and quantum applications. These are great, rapidly growing markets that require power electronics and optoelectronics. And lastly, there's a lot of synergies between telecoms and defense. So again, another opportunity here for sort of hybrid integration of compound semiconductor die to produce advanced modules for defense applications. So they're just some of the focus areas where we see that we should be driving forward and looking for international collaboration to take these ideas forward. So I'd like to sort of conclude my presentation with some articles here. We have these are clickable, so there are links embedded within the presentation. And just finally, just to thank you for the opportunity to present at SEMICON 22. So really a real great pleasure to present at this particular conference, and thank you. I look forward to your questions.